So in this talk, all graphs we'll be considering are undirected and either unweighted or non-negatively weighted. And one problem we'll consider is the global min cut, which is given a graph, delete the min number of edges or min weight of edges to just disconnect the graph. So disconnect any two vertices S or T from each other. And a very similar problem is the ST min cut, which is fix two vertices S and T, find the min cut that disconnects S and T. So for example, for this graph here, this cut denoted by just this single edge, whose sides are the left and right. This cut has size 1. It's a min ST cut and also a min global cut. And a well-known theorem for ST min cuts is that for any S and T, the ST min cut equals ST max flow. And moreover, given an ST max flow, we can recover the ST min cut. So to solve ST min cut, it suffices to solve ST max flow. So at first glance, it's not clear which problem is easier than the other. Like we consider the global min cut problem and the ST min cut problem. Some easy results that are known is that given an ST max flow algorithm, we can solve the global min cut algorithm, the global min cut problem by just, let's say, running ST max flow for all pairs S and T. This will be like n squared max flows. A smarter thing to do would be to fix just any vertex S and try all vertices T and compute ST max flow. This will also work because we want to just hit both sides of the min cut. And this takes n minus 1 max flows. But since we're aiming for efficient algorithms here, n minus 1 max flows is not ideal, and we want to do better. So there's one special algorithm that's based on push relabel that is able to compute the global min cut with using a single max flow. However, this is specialized to push relabel, and it runs time mn. Since then there has been algorithms specialized for the global min cut problem that do not work for ST min cut. But for these algorithms, the best running time is also mn, until Carter came along and introduced the idea of randomization to the problem. So his famous randomized contraction algorithm runs in time roughly n squared. And he also has an algorithm that essentially runs in near linear time based on random sampling for graph specification plus a tree packing approach. And this essentially is optimal up to polylog factors. But the point is, these algorithms are both randomized, and the best deterministic algorithm known so far is still mn time. So this leaves a few open questions. So first of all, in the randomized case, the problem is being solved, a near linear time algorithm is known. In the deterministic case, can we find a near linear time algorithm that solves this problem deterministically? And finally, running time aside, it would be nice if we can relate the global min cut problem with the ST max flow problem in a more tighter fashion. Let's say, can we compute a global min cut using just, let's say, polylog max flows? This will be like a more concrete way to say that the global min cut problem is no harder than the ST min cut problem up to this polylog factor. So these are the main problems we'll be considering in the talk. Can we solve min cut deterministically in a faster running time, ideally near linear? And also less about running time, a more conceptual problem. Can we solve global min cut in just polylog and ST max flows, plus some like very basic, let's say near linear time pre-processing. So these two problems have had no progress from the 1990s until roughly 5 years back, where a breakthrough result of Karabashi and Thorup showed that actually partially resolved the second open problem and showed that deterministic min cut for simple graphs can be solved in near linear time. This should have been tilted here. So a simple graph is just an unweighted graph where there are no parallel edges. And since then, so this running time had a large polylog factor. This has improved since then. But still, no progress has been made in the general weighted case. And this is where this work comes into the picture. So we show a deterministic min cut algorithm for weighted graphs in near linear time plus polylog calls to max flow. So we partially resolve open problem 2. We make progress, but it's not at the near linear linear time yet. And for problem 1, we essentially resolve this problem to show that the global min cut problem is no harder than the ST max low cut. So our approach is based on two simple ideas that are more prevalent in modern algorithm design. The two basic pieces are we design a local algorithm for the min cut problem, and we apply expander decompositions on our input graph. So these techniques have seen a lot of action recently. They were initially popularized by Spielman and Tang in their near linear time algorithm on solving Laplacian systems on graphs. So you can think of this as like a more modern approach to algorithm design. These are more modern ideas that were not known 20, 30 years ago. I want to briefly go over how these techniques are used for graph algorithm in general. So this is going beyond just the scope of min cut as a problem. So I'll be covering how these techniques have been used in the past, famous results that have been achieved based on these, and how one might use them for future problems. So for the local algorithm side, the basic concept is as follows. So given a graph, let's fix a seed vertex S. So just some vertex S. If there is some good cut local to, if there's some good cut for some problem that we won't specify, that is local to S in the sense that the smaller side of the cut contains S and has a small number of, say, vertices or edges, then we want to output the cut or a similar cut in time sublinear in the entire graph. So essentially, we don't want to look at the entire graph. We want to run in time sublinear in, say, the number of vertices or edges of the graph. So you think of, ideally, we would run in time roughly the size of the smaller side, the side containing S, because we need to output that for the problem. So optimally, we will be running in just that time itself. So this technique has been used in the now well-known Panigrahi-Nibble algorithm, which is a local algorithm to compute an approximate low conductance cut in the graph. So PageRank is the well-known Google's web page ranking algorithm, which has been analyzed theoretically. And Anderson, Chung, and Lang have shown that you can use this concept to develop a local algorithm for low conductance cuts. And the running time is ideal. It's roughly the number of edges in the smaller side. And this work, how we use local algorithms is we show the following theorem. If the global min cut is very unbalanced in the sense that it has only polylogarithmic vertices on the smaller side, like this, then we can essentially find it in polylogarithmic ST max flows. So why is this local? Essentially, we want to find a seed vertex in S. But since S is small, we might need to guess many seed vertices in the graph. Now the point is, we're not running an ST max flow procedure for every single seed vertex we guess. We're saving our work and showing that we can run essentially a local max flow algorithm from all the seed vertices at once in polylog ST max flows total. So you think of every single seed vertex has an amortized sublinear time. So that's the first concept we use. The second technique we're going to use expander decomposition. And here the concept is very simple. There's just two steps. First of all, let's suppose as an easy case that the graph is an expander. So for a lot of problems, when the graph is an expander, the problem becomes a lot easier. And for general graphs, the idea is going to be, let's just decompose the graph into expanders. So partition the set of vertices such that every vertex set induces an expander. And let's say there are not many edges between the expanders. And then we'll solve the problem on each expander and somehow recurse on the rest of the graph, the vertices between expanders, which will be, let's say, a constant fraction response. So the problem size drops by, let's say, factor 2. Of course, how we recurse and how we stitch together the problems is problem specific, but this is the general approach. So first of all, in order to even make use of this idea, we need an efficient algorithm to compute expanded decomposition. So this has been known for a few years back how to do randomized, but recently in this Fox, myself and Jujoy, Gao, Nanangkai, Peng, and Saranarak has shown that actually we can do this deterministically in nonlinear time. So this essentially opens the path of expanded decomposition in deterministic graph algorithms. Now, why are expanders? So first of all, for the min-cut problem, we had to answer the first case. Why are expanders easy for min-cut? Well, it turns out if the graph is an expander, then the min-cut must be unbalanced. So we'll see this later on. We'll define expanders more formally later on. The point is, in expander, the min-cut, the global min-cut must be unbalanced. So therefore, the local algorithm works. Okay, so that's it for the general high-level overview of the both techniques. Now we'll dive deeper into how these techniques are used for the specific min-cut algorithm and how for the specific min-cut problem and how our algorithm works. So for a local algorithm, our main insight will be this concept of isolators, defined as follows. Suppose S, so here S is the vertices on this side of the green cut. S is a min cut of the graph. Then a subset of vertices T is called an isolator if S intersect T has size 1. So it's exactly one vertex isolated. So essentially S, the smaller side of the min cut, isolates one vertex in T. That's the way you can think about it. So our main result for isolators is that given an isolator T, actually given any T, not necessarily an isolator, a subset of T vertices, for each vertex T and T, for each vertex little t, we can compute the min cut that separates T from the rest of the vertices in T. If we do this over all T in a total of essentially log n total max locals. So we do this for all T. So you can think of this as an amortized sublinear time over all T. So for each T, we're paying essentially amortized sublinear because we're paying only log T many total max locals. So here, the purple lines show the min T and the rest the T and T minus T min cuts. So and the idea is like this is true for all T, but if T is an isolator, then one of the cuts returned, one of the T and T minus T min cuts we return is the min cut. So we'll briefly go over how this algorithm works. It's actually very simple. So here's the algorithm essentially. So again, we are given as input the subset of vertices T. We're going to compute bipartitions of T, some log T many times. And the point is we want the bipartitions such that for any pair S and T, it's separating at least one of the bipartitions. So for example, we can compute x1 and y1 like this. We can compute x2 and y2 like this. And these two bipartitions ensure that any two vertices S and T in T are separated in at least one of them. So one deterministic way to do this is we can just encode the vertices in T using in binary. And then for each bit position K, just let xk be the vertices whose encoding has a bit 0 at the case position, and yk be everything else. So this will work. But that's not the point. The point is we just want the separating property. And then for each such bipartition, we compute the min cut separating the xk and yk. So this is just the min cut such that all vertices in xk on one side and all vertices in yk on the other side. So these are the min cuts for x1, y1, and x2, y2. And finally, let's take the union of all the edges in the min cuts. So what I want to claim is once we remove these vertices from the graph, these edges from the graph, the union of the min cuts, this essentially breaks the graph into disconnected components, into connected components, such that every connected component, such that every vertex in T belongs in a unique connected component. So no connected component has more than one blue vertex. And this is true because if a component had more than one blue vertex, then well, there was some min cut that was separated these two vertices because they were on opposite sides of some bipartition, so they could not have been on a single component. And now the key property we're going to use is that, so here the green boundaries essentially like the green curves here mark the boundaries of each connected component. And the key claim we're going to use is that for each vertex T in T, the min cut separating T from the rest of the vertices in T is contained in its connected component. So like this. So here the purple the cuts are the min cuts separating each vertex T from the rest. And each of these cuts is essentially contained in the outer boundary that marks the green curve, which marks the outer boundary of their component. So this is done using a simple uncrossing argument that is popular in graph cut algorithms based on this idea of some modularity of cuts. And finally, this is nice because what we can do is we can, for each vertex T, we contract everything outside of T's piece and just into a single, let's say like a gigantic blue vertex, and just run max flow, run SE max flow where S is the vertex T and T is this giant blue vertex. And now here, the key observation is that the sum of all the max flow instances over all T is O of M. The size of all the sum of the sizes of all the instances O of M. And that's because every edge in the graph can belong to in at most two components. Right? If the edge neighbors two different pieces, then it's counted twice. If the edge is inside a single piece, then it's counted once. So the point is the total sum of the max flow instances, the sizes of them, is O of M. Okay, so before we go to the expanding component part, let's just show that this simple idea immediately implies a simple randomized min cutout, a global min cutout. So there's randomness here. And the idea is basically is very simple. Consider the min cut, and let's say S the smaller side. Let's guess S to be roughly size 2 to the I for some I. So we'll just try all I. Now we sample each vertex with probably 1 over 2 to the I. Now with constant probability, we sample exactly one vertex in S. So with constant probability, the sampled set T is an isolator. So we can just try this like log n times when we find one with high probability. And we just run the isolator out. So this is a very simple randomized min cut algorithm that requires polylog and ST max locals. So unfortunately, de-randomizing that algorithm is not as straightforward. The issue is when the sampling rate is very small, and those are particularly hard to de-randomize. So we need a new idea. But in the case where the sampling probability is not so small, so in this case, let's say T is called an almost isolator. If S intersect T has not size 1, but size, let's say, polylog n. In that case, the subsampling rate is just 1 over k, which is like 1 over polylog n, which is not too small. And this can be sufficient to de-randomize. So this is like standard techniques of de-randomization. This can be de-randomized with an overhead of poly k times log n. And since k is only polylog n, this is still polylog n. So by overhead, I mean we'll compute a deterministic set of subsets of T. So T is an almost isolator. We compute a set of subsets of the almost isolator, such as one of these subsets is guaranteed to be an isolator for any set, essentially for any set S of small enough size. So this essentially solves the unbalanced case that we've highlighted before. Suppose that the min cut S has let's say polylog n vertices on the smaller side. Then by setting T to be the entire vertex set, this is already an almost isolator. And then we can de-randomize the subsampling procedure, and we get an algorithm that uses polylog n max flows. So this already solves the unbalanced case. So the balanced case requires more work because again, we cannot de-randomize very small sampling probabilities. So in this case, let's suppose that we are in the unbalanced case, so that both sides of the min cut have more than polylog n vertices. And for simplicity for this talk, let's assume that T is just a vertex set B, original vertex set B. Our goal here will be we're going to essentially vertex sparsify T. So we're going to find a subset T prime of size at most half of T, such that we still want what we still want is we still want T prime to hit both sides of the min cut. So S and V minus S both include and still have at least for one vertex in T, right? Because once we don't have that property, we're kind of dead because we don't have a single hitting vertex on one side of the min cut. So we still want this property, but the point is we're sparsifying T so that this sparsification can only happen like log n times before we're done. So now, assuming this sparsification, our algorithm should be very simple. We're going to start with T to be the entire vertex set. We're going to run the unbalanced case and just compute a cut. This might not be the min cut if the setting is actually balanced, because we don't know which case it is. We just run the unbalanced case, and then we sparsify T. And then T is now a sparsified set. We run the unbalanced case again, and we keep on sparsifying and keep on doing this until, let's say, T is size 1. And we return the smallest cut we found in any of the unbalanced cases. So the point is, in at least one of these cases, we will in fact be in the unbalanced case, and that cut will indeed be the correct cut. So it should be clear this algorithm is correct. Okay, so now let's go. We're going to go through the concept of expanding decomposition and how we apply it. So before that, let's just give an overview of what is an expander and what is the conductance of a graph. So conductance of graph is just this expression here. We're minimizing over all S such that the volume of S is smaller than the volume of the complement, where here volume means the sum of the degrees of the vertex in S. So now I want to prove the following claim I stated before, which is essentially for the min cut problem, expanders are easy. And the claim I want to make precisely is that if the graph is a phi expander for some phi, let's say polylog n, actually it should be 1 over polylog n. So this should be 1 over. Then the smaller set of any min cut has size at most 1 over phi. So the proof is essentially going to use this conductance property. Let's suppose that, let S be the min cut, and suppose without loss generally that S has, the volume of S is smaller than its complement. Then the volume of S is sum of degrees. Now every degree is at least lambda, where lambda is the min cut, because every degree is a valid cut in the graph. And that's lambda times the size of S. And now the conductance, phi, is at most by this definition. Now here, by definition, S is a min cut, so the number of edges is equal to lambda. And then the volume is at least lambda times the size of S. And this translates to S being at most 1 over phi. Which is a very simple calculation that shows that for an expander, we're in an unbalanced setting, and we can just run the local algorithm. So what if the graph is not an expander? Then our idea is going to be, let's compute an expander decomposition of the graph, which is more formally, now we'll finally define it, we partition the vertex set into some V1 all the way to Vk, where k is arbitrary, such that each induced graph on each part is a phi expander. And moreover, at most half of the edges go between expanders. So half is arbitrary. We just want the size to essentially go down by a constant factor each time. And for a min cut application, our two key insights are as follows. Any min cut cannot cut too deeply into an expander, into a part. By that I mean, take let's say the smaller side. So take any expander, take the min cut, and take the smaller side of the cut within this expander. By the same argument as I did previously, we can show that there are most 1 over 5 vertices on the smaller side. So we cannot cut too deeply into expander, regardless of how large the size of the expander might be. So this is insight 1. Second insight, which I won't prove, and this requires a little more work, is that a min cut cannot cut at all into too many components. So, so more formally, there are only 1 over 5 components where there's at least one vertex on both sides of the min cut. So that I won't prove. That's a little more technical. But now the point is, given these two insights, the idea is going to be very simple. Take each expander and just select an arbitrary small set of vertices inside an expander. That will be our sparsified set, T prime. We just select an arbitrary set of vertices in each expander. Now, Now the intuition is going to be take an expander. Suppose we sample like more than 1 over 5 vertices. Let's say 1 over 5 plus 1 vertices. Then if we're unlucky, we might sample, let's say, all the vertices in the smaller side when we take the intersection with the min cut. But since we sample strictly more than 1 over 5 vertices, then we're guaranteed to find one vertex on like the correct side of the min cut. Okay. So that's it for the algorithm. So the summary is, again, we showed a deterministic min cut algorithm that runs in like roughly near linear time, plus like a polylogarithm calls to SE max low. And the main open problem is, can we achieve near linear time regardless of how long max low calls take? So can we just compute deterministic min cut near linear time? And one nice thing about the concept of isolators is it has other applications. For example, consider the problem of Steiner min cut, which is given a graph and a subset of vertices called the terminals. Find the smallest cut in the graph that separates at least 2 terminals from each other. So this is just the min cut problem where the Steiner vertices are all the vertices. Sorry, where the terminals are all the vertices. Where the terminal set can be much smaller. And this problem we show is also equivalent to essentially polylogarithm max lows, at least with random sampling. In deterministic setting, we also have this extra m to 1 plus epsilon factor. And so we think that there might be other applications of this concept of isolators for other like graph cut problems in the fast algorithm setting. Yeah, so that concludes my talk.